Hello, everyone. This is Professor Ma, and this is the sections on continuities. In these sections, we will use the language of limits and to make or to define what we mean by some graph is continuous or not continuous. Okay, and obviously we know what intuitively geometry what continuous is. This is continuous, and this is not continuous. It's broken. Okay. So over a domain, if in this case, from here to here, the domain D, we say this is continuous in D, in domain D. And suppose the domain D over here is broken, we will say this is discontinuous in D. Okay, continuous in some domain D. Okay. In particular, there will be a point where it's broken. We will talk about discontinue at the point x equal to a. Okay, so we're going to use the language limit to define what's intuitively that match our things that's broken or not broken. Okay, so if a function becomes in a graph disconnected at a point x equal to a, we say the function of course is disconnected. Okay, and let's start with how we do this. And here's the functions. Okay, we'll let f of x to be defined to be on the right hand side to be 1, and at 0, 0, and on the left hand side minus 1. Okay, this is a highly disconnected two pieces of line. But if the domain is defined over the entire real line is disconnected, is discontinuous. But if I only look at the left hand side, okay, it's continuous on the left hand side before 0. Okay, it's continuous on the set on the positive side too. When I'm trying to show the red line, it's continuous. If I just show you that portion. Similarly, only show the left and blue portion. Oh, that's continuous. Only if I show you the entire thing, it's discontinuous. 0. Okay. So how do we classify these with limits? That is, these visual observations of these continuities, broken lines. How do we use algebra to check it? Here. We imagine, what do we mean by discontinuous? So we imagine, for instance, on the right-hand side, and then n is crawling on the right-hand side. It's continuous, so it's, think of that every dot, it's a little brick on the walkway, so it's walking along the red lines, and it's continuous to everything positive. Okay. Until you get to the point 0, 1. Okay, as x go to 0 from the right hand side. Okay, you will find out the end at the point x equal to 0. We will find out that point that is expected is supposed to be filled in. It's not there. It's expecting the limit of the coming from right hand side is equal to 1. Okay, the limit. But at the point itself, x equal to 0. Okay, these notice 0 and the limit coming from the right hand side x equal to 0. At 0 itself is 1. Okay, it's not there, but rather at 0 is defined to be 0. Therefore, it causes this jump. And that's why it's discontinuous. Okay. So let's be a little more precise about this. So let's look at a little simpler versions. Okay. We're going to define something a little bit more clarified, a little more clearly. Okay. Suppose we have these functions, and the ends coming from the right-hand side, the limit. So in other words, what I mean by that is a limit x go to 0 from the right-hand side, positive, of g of x. Okay. What does it equal to? Well, the end say, well, the height is always 1, so the limit, of course, is 1, right? On the other hand, notice the point at 0, okay, is 1. They're the same. Hence, the end, so on the right-hand, so from coming from the right-hand side, its limit is equal to the function value. In this case, it's sealed, if you like. It's closed up. It's supposed to be there, and in this case, we say the function's right continuous at 0, coming from the right-hand side, the plus side, the positive side. It's right continuous at 0. But if you were to do this on the left-hand side, okay, and it's expect to see -1, but the function value at 0 is not -1. It is positive when it's up. It's given to the red line. So therefore, it's not left continuous. Okay. So we say a function is right continuous if the limit of function coming from the right-hand side of the number is equal to the function value you plug in. The picture is exactly that. We say the function is left continuous if coming from the left-hand side of A is equal to the, suppose that this function, then coming from the left-hand side, okay, of 0 is equal to -1, because I define 0 is to be -1. This function is left continuous. Okay, so we define this right continuous and left continuous. And the one we start out with, this one is not left continuous nor right continuous. Okay, so you have these cases where you can be function defined is not right continuous, not left continuous at a broken point, or it could be right continuous but not left continuous, left continuous but not right continuous. Okay, so these are the summary. Right but not left continuous, left but not right continuous, not right or left continuous. Or it could be the right limit and the left limit coincide. It's right continuous and left continuous. At the point, they both come to the conclusion, same limit from left and right. In that case, we say the function is continuous. Okay, so this is a definition of what we mean by a function is continuous at a point. The left limit and the right limit are the same. Okay, so algebraically, to check for limits, we take left limit and right limits, okay, and compare with the function output itself by plugging the number. If all three of these coming from the left, coming from the right, and if I plug it in, it's at that point, then we say these functions continuous. Okay. Notice in these functions, okay, if I were to remove these, okay, I can fix it up. Let me actually remove completely. So suppose a function is defined with a missing point like this, okay. And we found that we can actually fill in the point and the kind of like two-side tunnelings, and they stop, and we find out we fill in the dots, and the two sides will be connected, right? This type of discontinuity we call it removable discontinuity. Okay. So but anyway, we'll talk about it in seconds. Okay. Anyway. To check continuities, we check the right limit coming in, the left limit coming from the left-hand side, okay? And I'm plugging the number a into the function itself. Okay, if they all coincide, this coming from the left, coming from the right, and this function value is at the blue dot is where it is, they all connected, therefore it's continuous. Okay, suppose it agrees on the right hand side, but not on the left limit, then this is the right continuous. Okay, that's a picture. And if it agrees on the left hand side, it's left continuous. And then you got a worst case scenario where it's, it's not left continuous, right continuous, so it's broken quite a bit. Okay. Now, notice these functions. If I notice the formula x divided by x, what does the picture look like? Well, its domain is everything except x not equal to 0. Okay. You cannot put 0 over 0, it's not defined. But this obviously, if I were to fill in a 0, then I can make the function continuous at that point. Okay, so this type of broken line where you can fill in an empty point to make the line continuous, we call this type of point removable discontinuity. Okay, a functions like what? X over x. 0 is removable. How? By defining x equal to 0 to be 1. So if I do that, then this point 0, 1 is part of this graph, then the graph is continuous. Okay. In picture, that's what we're doing here. In this type, none of this is removable. Okay. It's the x to 0, not non-removable. Okay, removable has to be very nice, just with a gap in between. Like what? Like these functions. Oh, not these ones. So this is an example asking you: is right continuous, left continuous? It has multi-rules functions, right? The trouble spot is x equal to 2. So. First, notice x equal to 2, that formula is actually x plus 2. So when I calculate the right-hand limits using this formula, x coming from 2 from the right-hand side, okay, and just plug in that, I get 4. Okay. Come from the right-hand side, just plus 2, plug in to 2, I get 4. How about coming from the left-hand side? 2. Coming from the left-hand side is, I'm using this formula. If you remember, then when x approach 2, this will go to 0, and this will go to 0, and then the limit is 1. Okay, if you don't remember that, look it up. Okay, it's 0 over 0, right? Okay. So the left-hand limit and the right-hand limits are different. Okay, in particular, the function value at the number 2. X equal to 2. Actually, it's 0. This 0 is different from the right hand, coming from right hand, coming from the left hand. And here's what it shows up on the graph. Coming from the right, coming from the left, and they all go to different places. Okay. Here's coming from the right is the function x plus 2, but you stop at 2. Because at function equal to 2, it becomes 0. It's defined such way. If it's coming from the left, then basically you have a curve look like that. Okay. So this is highly disconnected at x equal to 2. Okay. It's not removable. Okay. On the other hand, okay, if you look at these functions, it's not defined at x to 0, so it has a hole there. But is that hole can be plugged in so that the thing become connected? How can I check that? Well, check the right hand limit total 0. Check the left hand limit. See if they are the same number. Okay, if they are the same number, that means they are going to be able to join at the number. So if I check, coming from, I can check both same time, x goes to 0, and if I multiply, remember, sine of x squared, x goes to 0, the sine of x squared is approximately x squared, and divided by denominator x. So this is approximately x, okay, if you like. And that's what it says, approximately. X goes to 0, so this goes to 0. So the right hand and left hand limit, okay, they actually go to 0. They go to the same y. Hence, I can define 0 to be 0 and plug in the hole. And so this is the function sine x squared divided by x. And if I define it to be 0 as 0, that I can plug it in. And now this becomes a continuous functions. And this becomes, this point is called a removable discontinuity. Okay? And there are many functions, for example, in mathematics, okay, has holes in which we can plug in and make it complete. Okay? Fortunately, this is not traditional sense of elementary function anymore, because there's extra step you have to fill in the hole. Okay, so many examples of about curves are made by this type of curve, that is, take elementary function and fill in the holes, and now we get an example. Okay, and so it is removable. Okay. Oh, this one, sorry, that's the last one. This one is not removable because sine of x is basically x. Okay, so x divided by x. This is basically the function y equal to 1 over x. And the right hand limit goes to positive infinity. Okay. And the left hand limit goes to negative infinity. Okay. So y from the right hand side, y from the left hand side goes, so it shoots up, and you cannot join them. You cannot join the two sides. The two tunnel, one goes out, one goes down. You're not going to be able to make them. So it's non-removable. Okay, and then another type of non-removable is that the left-hand side and the right-hand side oscillate as they get close to the that point at 0. So the examples like sine 1 over x, okay? When x approaches 0, sine 1 over x begin to oscillate, okay? You know, and choose x to be 1 over pi, 1 over 2 pi, sine pi over 2. You can choose. So good. I like to choose, find the values that so you keep hitting 1 minus 1 1 1 minus 1 4. You can choose the x values. Okay, so the graph begin to oscillate wildly, and it's non-removable. It's not defined as 0. Okay, so but there's no way you can fill it in a number, so the whole thing is connected. Okay? Because on the left hand there's no limit, right hand there's no limit, left hand there's no limit. Okay. Non-removable as 0. Okay, so that's it. That's about continuity. Okay, bye bye.